Okay, in this diagram, we have light waves that are traveling towards a double slit. When they go through the double slit, they'll diffract through both, and then they'll overlap like so. So if I put a screen all the way down here, they'll form a pattern like this. This is known as a double slit interference pattern. As you can see, there are a bunch of maximas, or sometimes called bright fringes, where the light is bright. And then you've got points of minimas where it's completely dark. It's not the light is not reaching there, it's just when the light from both slits meets there, it's just cancelling out and this destructive interference is occurring. Okay, firstly, for an interference pattern like this to be formed, the light that's hitting the double slit needs to be coherent. Coherent means that firstly it's monochromatic, meaning it's the same wavelength or frequency hitting both slits. Okay, in this case I'm using red lights, which is a single wavelength. And secondly, it needs to be a constant phase difference between the light that's hitting the slits. Let's call this slit X and this Y. So if the phase difference between the light hitting X and Y is in phase, like is shown in the diagram here, then it needs to remain in phase while for the pattern to be seen on the screen. If for some reason the light hitting X and Y has a phase difference of, let's say, pi over 2, as long as that phase difference remains pi over 2 and is constant, that phase difference, then a pattern can be seen on the screen. It might not look a bit like this, it might be shifted left or right, but a pattern would still be formed. Okay, so we're asked to explain why the second bright fringe is formed in the Young's double slit experiment. Firstly, we've got coherent light hitting the double slit, and it's going to diffract, it's going to spread out and overlapping, and it's going to meet at some point on the screen. So we are asked to explain this one here, not the first, the central one, but the second bright fringe. Okay, so firstly, they're going to meet there with some kind of path difference. The middle one here, it was formed because the wave both traveled the same distance from the slits, and so they would have met with zero path difference. The second bright fringe would have been formed because they would meet with a whole wavelength of a path difference. So the path difference there is a whole wavelength. That means they're going to meet in phase. The phase difference is going to be zero. Okay, so when they meet, they're going to superpose the two light rays there, and they're going to superpose constructively because they're in phase. Okay, so they'll add up and they'll give you a maximum like this. Okay, so now we're trying to explain how the third minima is formed. Now it doesn't matter which side I look from, but I'm going to look from the bottom one here. That's the first minimum, that's the second minimum, and that's the third minimum. So obviously coherent light goes to double slit, it diffracts and it overlaps and is going to meet at some point here. So here, this is where the third minimum is formed. Okay, so firstly, the first minimum is formed because the wave traveling from the top slit would have traveled 0.5 wavelengths extra. The second minimum is formed when it's traveled 1.5 wavelengths extra. So the third minimum is formed when it's 2.5 wavelengths. Because if it's 2.5 wavelengths, the same as basically saying half a wavelength, and it's going to be an antiphase. So when they superpose, they're going to superpose destructively, forming that minimum. Okay, in this question, we've got a light source which is used to eliminate a double slit. Suggests why an interference pattern is not seen on the screen. Suggests two possible solutions. Okay, so one of the reasons why there might be no interference pattern is because maybe the light source isn't coherent. Okay, so how can we make it coherent? One way would be to use a single slit and pass the light through a single slit before it hits the double slit. Okay, so this means that the single slit will act as a point source, and when the light arrives at the double slits, it's coming from a single point. So the phase difference at that point will be a constant phase difference. Okay, also if it's not monochromatic, we could also apply a filter in front of the single slit to turn it into a monochromatic light as well of a single wavelength. Okay, a second solution is to just replace the light source with a laser, because lasers always produce monochromatic coherent light, and in that case you wouldn't even need the single slit. You can just direct it directly at the double slit and you get an interference pattern. Okay, in this question, we've got monochromatic light from a source is incident on a double slit as shown below. The phase of the light arriving at slit S1 is pi ahead of the light arriving at S2. Okay, so this is pi ahead. Okay, so that's because it's being directed at an angle. The wavelength of the light is 600 nanometers. Which of the following best describes the observation at point X? So first option is interference pattern is not formed as the light incident is not in phase. Okay, so this is not a requirement. It doesn't need to be in phase. It just needs to be coherent. And for it to be coherent, it just needs to be monochromatic, and there needs to be a constant phase difference. Okay, they don't need to be in phase as long as the phase difference is constant. And in this case, there is a constant phase difference, is pi ahead, so that's fine. So this is not the answer. Okay, a maximum is formed, or a minimum is formed. So to do that, we need to check the path difference. Okay, so let's figure out the path difference. So that gives me 900 nanometers. Okay, how much is that out of the whole wavelength? So that is 600. So 600 is the wavelength, so that's basically 1.5 wavelengths, which corresponds to 3 pi. But keep in mind, there's already a path difference of pi. Okay, so we need to add that on, extra path difference there that it's arriving with. So that means the total path difference is 4 pi, which is the same as saying in phase. Okay, so that means a maximum is going to be formed. So this is the correct option here. And which maximum is it? Well, it's not the central one, not the first one, because the second one, sorry, because that would be 2 pi. So this is going to be the third maximum.